Hi everyone, welcome back to another session of the Encode Polkadot Educate series. Today we have a really interesting talk from Alberto Viera from PaperMoon, who I'm going to invite to the stage now, who's coming to us on holiday. So thank you so much for joining us today, taking time out of your day.
It's great to be here. I'm Alberto from PaperMoon. PaperMoon is a company that provides developer relations as a service for Moonbeam. I've been with Moonbeam over 4 years already, so 4 years as part of the Polkadot ecosystem. And yeah, today I'm going to be talking about a high-level look at asynchronous backing from a Parachain perspective. So, I mean, don't expect this talk to be like a deep dive into the code of asynchronous backing. As you know, I'm not a software developer, but it's more like a high-level overview of how it works. Why is it important for parachains? And some sort of improvements that we see when we implement async backing, and some things that we would like to see in the future to actually, boost the performance a little bit more. So yeah, let's get started. By the way, feel free to put questions in the chat. Rebecca's going to help me on chiming in the questions because I'm only one screen setup, and I'll try to go back to the chat just to see if there's any interesting questions as well popping there. So. First, let's start with what is a parachain, right? We're going to start a little bit sort of out far away from async backing, and we're going to start sort of going into async backing, but I think we need to set up some concepts first. And so let's talk about what really is a parachain, right? So a parachain is a blockchain that runs in parallel within Polkadot, right? In Polkadot, you have the relay chain, which is the Polkadot chain itself, and you have many parachains running in parallel. And each parachain has its own state, right? So if you have a parachain that is smart contracts like Moonbeam, Moonbeam has its own set of accounts, balances, and everything like that. It has its own set state, right? That is independent from other parachains. A parachain has also its own state transition function. So this is basically, it means that each parachain is a heterogeneous shard, meaning that the state transition function, it's different or could be different, right? So if you have a parachain like Moonbeam, Moonbeam has its own set of rules on how you change one state to the next in a block, okay? And then you have other parachains like Hydration or A-Star or other parachains in Polkadot that have their own state transition function, right? Like their own ways of migrating state from one block to the other. What's really interesting is that the Polkadot relay chain secures all these parallel blockchains because they can actually, the Polkadot relay chain stores the state transition function for each of these parallel blockchains, okay? And so the relay chain can actually verify that the state transitions are valid, okay? So if you have one state, it can verify that if you apply these certain transactions to that state, the calculated state by the parachain, it's okay, but it doesn't check that the actual state is valid, okay? And that's why we've seen problems in parachains happening at a parachain level, that it doesn't mean like Polkadot didn't do a good job, right? Because the state transition was actually valid. It was just a problem in the state transition that resulted in a bug in a parachain, okay? Parachains themselves are in charge of producing blocks. They're not in charge of security, and the relay chain is what is actually checking the security or the state transition that is valid. So, what is a parachain block, right? Now we know high level what is a parachain. Let's now do one step into the parachain world, which is a parachain block. Put it in very simple terms. Like I said, I don't do deep dive into every single parameter, but a parachain block contains a header and a body, okay? A header contains the metadata of the current state of the network via state root hash and things like that. And it has references to the parent blocks, enabling block verification and integrity, right? We've always heard the term blockchain, and the reason why it's blockchain is because you have information from the previous block and the next block and so on. So it creates a chain of blocks that all are interconnected. And so the header is basically a summary, if you want to call it like that. It's a summary of everything that has the blockchain has, okay? The header doesn't contain that Alberto has this balance. The header contains that if you grab all the balances of all the accounts, it should result into this hash, and that's what actually is verifiable, basically. the block body can be seen as, simplifying it as a list of all the state transitions, okay? So you can see it as a list of transactions, and each transaction is basically telling the blockchain that you want to move the state from one value to another, okay? So an extrinsic or a transaction is basically a request to do a state transition within the blockchain, okay? And so, in substrate-based chains, you have multiple type of extrinsics or transactions. You have ones that are executed when the block is starting to be executed. You have then the transfers that are made by regular users or signed users. And then you have transactions that are done at the end of the block execution, okay? And then talking about block execution, all transactions need to be executed within a limited execution time, okay? So, this is similar to the concept of Ethereum that it's gas, right? So everyone knows that Ethereum has gas, and then within a block, you can execute more or less, it's dynamic, but let's say 50 million units of gas. And then that is basically can be 2 transactions if they're really heavy, if they're really computationally expensive, or they can be 1,000 transactions if they're very, very simple transactions. This is similar in Substrate or Polkadot SDK-based blockchains, but we use a term called wait, which is the time in picoseconds that a certain transaction takes in a reference machine. I always joke that it's like a machine that is running Windows 98 and Intel processor and 2 gigabytes of RAM. It's not like that, but you have a reference machine, and then you measure in that machine how long it takes to do a balance transfer, and then you say, okay, it's 2 milliseconds or whatever. Okay. What's important is that you set each blockchain has a limit, right? It has a limit, a physical limit of how many seconds it has to execute the transactions. And this is important because the relay chain also has that same limit, okay? So when the validators on the relay chain on Polkadot are verifying the block, they need to be able to execute that block within the time limit, okay? Cool. Parachain block validation. Now we're almost getting into async backing yet. So I want to really give a lot of credit to the following article. I think this was written by Joe Petrowski, but this article is not new. It's at least 2 years old. I think even more, maybe 3 or more. It's really well written, and it takes you through the path of a parachain block. Okay, it takes you to in really high detail, like what's the process of a parachain block when it goes through the relay chain. Okay, and I'm gonna summarize it here basically. So giving credit where credit is due. And so a parachain block, there is a relationship between parachain collators, which are the block producers that are producing blocks in the parachains, and Polkadot validators, okay, which are the validators that are helping secure Polkadot and also helping secure all the parallel blockchains within Polkadot. And so the parachain block validation can be divided at a high level, right? Like I said, I'm not going technically terminologies. This is not probably 100% correct, but high level explanation. It has 3 main steps, which is block backing, block inclusion, and block finalization, okay? And so in block backing, basically, there's a subset of validators from the Polkadot relay chain, you can see here on the right-hand side, that are randomly chosen to verify a block that is produced by a collator in the parachain, okay? And so we can call this a para block. And so this doesn't ensure parachain block finality, meaning that these validators could be malicious, but Polkadot has multiple lines of defense to ensure that if these validators are malicious, that means that there's other ways to cache these malicious blocks, basically. Okay, but basically, parachain block backing at a very high level, it's a process of a subset of validators will connect to the collators and will verify the state transition. And we're going to go into a bit more detail of how they do that. And then they do what is called the parachain block inclusion, in which they say, okay, this block is valid, so I'm going to start spreading it around the Polkadot set of validators. If you want to read more about erasure coded chunks, which is super interesting, I've left some links in the slides, and at the end I'll share the slides. But basically, the erasure coding chunks is a way that you start spreading block information, not the state itself, but just the state transition and other kind of details. You start spreading it around the validators. And then at any point in time, if a validator can recover what it's called the block details for verifying the state transition, by getting a third of these chunks, okay? So it's kind of like Horcrux, in which to recover the entire thing, only you need a third or whatever portion, depending on how it's set up. And so the parachain block inclusion is kind of like a two-step process, okay? These validator subsets start spreading these erasure coding chunks among relay chain validators, but then also the relay chain validator that is going to propose a relay chain block will include a parablock candidate receipt, okay? So this is when now in the relay chain block, you have a parachain block information, and that's going to be included into the next relay chain block that is proposed in the Polkadot relay. And last but not least, you have the parachain block finality, right? When the parachain block is finalized, meaning that you cannot revert it anymore. There's no way of going back in history. When the relay chain block where the parachain block information is finalized, okay? So when Polkadot finality gadget says this relay chain block is finalized, and that relay chain block included information of a parachain block, that parachain block is finalized, okay? So this is basically like a three-step process. You have the backing, the inclusion, and then the finality. And this is important because that is similar to the article that I shared, the path of a parachain block through the relay chain, how it goes through the relay chain. So I'm going to stop here just to see if there's a question. Oh yeah, there's many comments on the chat.
Not questions yet, just some good mornings. And I've posted the article that you referenced.
Oh, thank you, Rebecca. That's actually pretty good because it's a super interesting article. So I appreciate doing that. Awesome. Okay, so now we know that there's three main steps. We're going to go into two of them only. Actually, one of them here, which is Polkadot parachain block backing. And in order to understand parachain block backing at a very high level, we have to talk about something called the POV, the proof of validity, okay? And so the proof of validity, it's the minimum amount of information a relay chain validator needs to check the state transition, okay? Imagine in a scalable blockchain, you cannot share everything, right? You cannot share, hey, validator, here's your state, here is the state transition, here is this, here is that, because everything happens super, super quickly, right? And so if you want to scale this operation, you need to be very, very efficient on how you verify with the minimum amount of information, how you verify that state transition is valid, right? So if I have 10 tokens and Rebecca had 0 tokens, and my state transition is that I'm sending her 5 tokens, right? And then the end result is 5 and 5, okay? That's basically it. And so in order to verify this, a validator needs the block, right? The list of state transitions that are included in that block that is being validated, which is kind of obvious, right? Because the validator needs to know what's going to happen, okay? Remember that the validator knows the state transition function, but it needs the state transitions or the extrinsics or the transactions to apply the STF, okay? And it also needs to know the state involved and the Merkle proofs, okay? So the Merkle proof is basically a way that you can verify state, okay? A state that is read on the blockchain. So it's really interesting. If you find Merkle proofs in Google, there's a lot of really good articles that do a much better job than me explaining this. But let's say I am modifying the state H of B, okay, which is hash of B. But let's say this is a state that I'm reading, okay. In order to verify this hash right here, all I need is the actual state. So the state here, the state B. I need the hash of the state A. I need the hash of the state CD, so I can hash this with this. Then I need the hash of EFGH. So I can hash this top here with this one, and then I'll get the end result, and I can compare that to what's being proposed by the parachain collator, okay? And so I can do my own calculations independently. I don't have to trust anyone. I do it, I verify, okay, this is good. Good job. I mean, you calculated the hash, the state root hash correctly, okay? And so all you need is the state involved. In this case would be my balance, let's say. And then you can hash that, right? And then all the hashes, what it's called the Merkle proofs hash, in order that you can calculate, or the validator can calculate the resultant hash and compare it, right? Everything else you don't need. So everything else that stays in purple here, you don't need. You don't need the hash of C, D, E, F, G, H. You don't need anything else. All you need is what I told you, right? The different hashes, okay?
Can I just interrupt you, because someone has asked in the chat, Saffron's asked, can you explain why you need H of C, D and E, F, G, H?
Yeah,
So
yeah, that's a good question, right? So all you want to do is verify, right? As a validator, you want to verify that this hash of A, B, C, D, E, F, G, H, which actually summarizes the entire state of the network, right? This is like a summary of the entire state of the network. Let's say my network only contains these 8 states, which would be really sad, but let's say for the sake of this example. And so if you want to verify that this hash that the collator is proposing, it's correct, and you know that the only state that was modified is the B state, right? You need there's a name for this in English that I'm not remembering, which is like the matching hash or whatever, okay? So you need the value of B, and then you hash it, right? And then you need the hash of A, so that you can compute, as a validator, you can compute hash of A and B, okay? And then if they give you in the POV, if they give you the hash of CD, then you can merge these two and hash it to A, B, C, D, all right? And then if the collator gives you this hash, then you can hash it with this one and get the end result and compare it. And you can say, okay, I actually calculated myself the hashes and I end up with the same result as the collator, okay? And so this means that the collator didn't cheat, right? Because remember that this hash right here, E, F, G, H, is a summary of everything that is underneath it, okay? If the collator tries to trick you in changing this value here will be different, and then this value here will be different because it's the hash of these two things combined, okay? And so hashing is a really good way to ensuring with a single 32 bytes component that everything it's solid, it's valid, that nobody cheated, okay? Because like I said, if you cheat and you change the value of E, so Alberto has now $1 million in balance, everything else will be cascaded down into this hash here, okay? Hopefully it's clear now, but if not, I recommend you to check. There's a lot of Google YouTube videos or Google articles about Merkle proofs that do a really good job in simple terms to explain how Merkle trees work and how Merkle proofs work as well, right? But hopefully that gives you some light.
Could you sort of clarify what's the difference between checking the work and checking the state?
Well, no, you don't check the work. I mean, you don't check the work. You just check that the end result that the collator is saying that he came up, right? Applying. So the collator says, hey, I have this state, I have this state transitions, and this is the new state that I'm proposing, right? And that is summarized in the block header, like I said before. The header has like a summary of the entire state of the network. And so all the validator needs to do, the validator is not going to check every single state to ensure that it's valid, okay? The validator only has to check the states that changed. And the only way the most efficient way well, not the most efficient way, but the way that this is done is by just getting the states that were involved, in this case B, because this is an example, and then the corresponding hashes that allow you to calculate this value, which, like I said, is a summary of the entire state of the network, which is basically the state root, okay? So this state root hash is a summary. This state root hash is basically this value here, and it's a summary of everything that cascades down into the state of the network. Note that in a real blockchain, there is many more leaves. So this tree, this is called a tree, it still grows a lot more and a lot more, and it has many thousands of components at the end of the day. Okay.
Thank
All
you.
right. Yeah, no worries. That's always a really good question. So hopefully at least it gives you some inspiration to do a better job like researching this answer. Okay. But what's important is that the validator can verify with these two components, it can verify the state transition. Remember what I said before, the validator will never check if the state is valid. It will check if the state transition being proposed by the parablock is valid, okay? Because the validator doesn't store the state of the blockchain, of the parachain. It only stores the headers, basically, and the state transition function. And so if the collator says, hey, I know that you have the header, which tells you the last summary, okay? I want you to verify this new one that I'm giving you with this set of extrinsics, right? And that's what the validator can do. And what's really important is that the validator has to do everything, the backing, within the block execution window, okay? So that's why the block execution cannot be 1,000,000 seconds, because it has a definite amount of time in which it has to do all this work to ensure that it can, keep going and validate another block and validate another block and so on, okay? So it has a very limited amount of time. And like I said, the validator doesn't have to write anything to storage. It only has to validate the state transition, but it doesn't have to calculate the new state of the blockchain. That is done by the collator itself. Cool. All right. So let's go into two things, right? Let's go into synchronous backing first, which is basically the opposite of asynchronous backing. I've left 2 more articles. Rebecca, if you can do me the favor, that would be amazing. So that you can do a more in-depth read on asynchronous backing, and also on Cumulus, which is basically the protocol of communicating parachains and relay chains and the consensus between parachains and relay chains. All right. So asynchronous process, it's a process in which it cannot run in parallel. It's a sequential process. And this is general. This is not in blockchain. This is in general, right? So let's say that you have the blue process and the purple process. So if the blue process is running, the purple process cannot be running. And then when the blue process or the cyan process ends, the purple process can start, and then so on and so on, okay? And so in synchronous backing in Polkadot, the parablocks depend on Polkadot progression, okay? Polkadot has to do, remember, backing and inclusion, and it does it in a sequential way, okay? So basically, it backs a parachain block, and then it includes it, and only after it is included, it can start backing the next parachain block, and then include it. And only after that one is included, then it can start backing another parachain block, okay? And so it's a sequential process that happens, synchronously, with synchronous, in a synchronous process, right? What's really interesting is that the backing and the inclusion each takes 6 seconds, more or less, in the relay chain, because it's backing happens in one relay chain block and inclusion happens in the next relay chain block. And that's why parachains that are not asynchronous backing, are not running asynchronous backing, can have a minimum of 12-second blocks, okay? And we'll understand this in a diagram that I'm going to show later. And so a new parachain block can only happen after the inclusion of the last one, right? So here you have a parachain block, here you have a parachain block, and here is basically 6 seconds. Parachain blocks are anchored to the latest relay chain block, and that's the main reason why it's sequential, because here, we're going to see it better in the diagram in the next slide. Let's just keep it that a parachain block needs to have a reference relay chain block, as it has some information about it. And so you can only produce a new one when you have a new relay chain block in your system, in your information, okay? And then, like I said before, it's backing and then inclusion, meaning that, you have to do backing before inclusion, and then it can happen in a single relay chain block. Hence, there is a 12-second delay between parachain blocks. So the diagram looks like this, okay? So let's say that you have relay chain block 0, and then you have a collator proposes a block here, and the relay chain validators start backing it. And then in the next relay chain block, which is now R1, it starts including it, okay? And so by the time this is included, the collator can propose a new block that is anchored to R2 now, okay? And then the process...
Can I just interrupt you with a question that I think might be important for understanding this if other people have it? Elle has asked, what does backing mean? So could you maybe explain backing and inclusion again, just so people understand?
Yeah, so backing is what we were discussing back here, which is the process of basically a subset of validators of the relay chain verifying that the block state transition is valid, that the migration of state within that block, it's okay. So the collator or the parablock producer was not cheating, okay? And so this is only done by a subset of validators from Polkadot. It's not done by the entire validator set, because if not, it wouldn't be performant. And then inclusion, just to summarize it, inclusion is the process of having information of that block that is really, really relevant to ensuring that the block is valid, the parachain block is valid, within a relay chain block, okay? And so that is basically the process of backing. Oh, sorry about that. Backing is the process of a subset of validators verifying the parachain block, and inclusion is the process. This is not, like I said, entirely true, but for the process of this talk, it's when the relay chain block, it's proposed for in Polkadot, and that relay chain block has information about the parachain block, basically, okay, that it's being proposed by the collator. And so these two things cannot happen within the same relay chain block. They have to happen in different relay chain blocks. And so that's why, if we go back to the diagram, you have the backing of the parachain block, which is this, what I said, that the verification by a subset of validators. And then in the next relay chain block, we actually are including information of the parachain block in the relay chain block itself, okay? And that happens in R2. So R2 has information about this P1 parachain block. And then that means that the collator can then propose a new block that is anchored to R2, okay? So the reference relay chain block is R2. But what's important here is that you can see that this is sequential, right? You have backing, inclusion, and then you can propose another parachain block so that it is backed and it's included. And then you can propose another parachain block that it's backed and included. And then within every window, you have 6 seconds. So that's why you have 12 seconds between parachain blocks, okay? And it's synchronous. It's not asynchronous. It has to, it cannot run in parallel, basically, okay? And so asynchronous backing at a, once again, high level, it's a process of running this system as an asynchronous process. And an asynchronous process is a process that can run in parallel, right? That's, I mean, hopefully you've ever coded in JavaScript. In JavaScript, you have the async functions in which if you don't put await, then the function keeps running, right? It doesn't stop in the execution. It can run many processes in parallel until you tell them, can you please await for this? Just, I need you to wait a little bit until my process is finished, for example, okay? And so an asynchronous process in the context of backing and inclusion, it's a process in which backing can keep happening, and then inclusion, so backing and inclusion of the same block is asynchronous. It cannot happen at the same time, but backing itself is a synchronous process, right? There can be many backings at the same time, and they don't have to be sort of like correlated to the inclusion, okay? And so now parablocks are not necessarily linked to Polkadot progression. And we'll see it in a diagram like the other one, which will be a little bit more clear. And so there is two main things to consider about asynchronous backing. Multiple parablocks can be anchored to the same relay chain block. So remember in synchronous backing that this block can only be anchored to a relay chain block after the inclusion of the previous parachain block. And in synchronous backing, that's no longer true. You know, this block could be anchored to R0, okay? And we'll see why. And the main reason is because collators cache parablocks informations at any stage of pre-inclusion, okay? So let me go back to the synchronous backing diagram. And so let's say this block right here, I had balance of 10 and I sent 5 tokens to Rebecca, okay? And so when this block is included, right, I can then propose a block in which the state is now 5 and 5, right? I sent 5 tokens to Rebecca, now we have 5 each. But what happens if I start producing a block that is referencing this R0 in which, according to history, I had 10 tokens and Rebecca had 0, but I am doing a transfer of tokens to Rebecca. So what happens now is that block producers have this information in cache, in memory, so that they can start producing blocks on top of these pre-included blocks that are not included in the relay chain, but we expect them to be included so we can build on top of them, okay? And so that you can now have blocks that are anchored to the same relay chain block, but that doesn't mean that you're gonna be cheating or you're gonna be building blocks that are invalid, because you're gonna be building on like these cached blocks that are pre-included, that they're not included yet, okay? And we're gonna see this in the diagram next. This is pipelining. Basically, this is asynchronous backing. So you have backing and inclusions for different parachain blocks can happen within the relay chain block, and we'll see that in the diagram. And this means that you can have more execution time. So before we had 0.5 seconds. So in 0.5 seconds, the collator had to execute all the transactions, okay? That's all that it had, 0.5 seconds, and it's actually a bit less than that. Everything would need to be executed, right? So if a balance transfer would take 0.1 seconds, only 5 balance transfers could be included in that block, okay? Now, if we're able to extend the execution time to 2 seconds, which is what async backing allows you to, now instead of 5, we can include 20, right? We have 4 more times of execution time, of block capacity, okay? But there's 2 diagrams. I actually like the next one a bit better, but this is a bit more high level, so it's actually pretty good, in which in synchronous backing, you had the parachain block 1 being backed and then included in 2 different relay chain blocks, and then the second block being backed after the inclusion of the first one and then included, okay? So you can see that this is a synchronous process. In asynchronous backing, you have parachain block being backed and then included, but then the parachain block 2 could be backed in the same relay chain block as P1 is being included, right? Because like I said, you can build this block based on what you know about this previous block, okay? And the diagram is really interesting because now if we don't take a look at the first line, because the first line has a small execution time, backing can now go over a relay chain block because it can be extended, because now you can start producing the next block without this block, right? I mean, so you have the possibility of start building blocks at different relay chain blocks and parachain blocks because everything is in memory, it's cached, right? And so you can start building valid blocks based on the previous history that is cached in your memory. And so you don't need to wait as a synchronous process. You don't need to wait for the previous block to be included. And so this allows you to run process in parallel, right? For example, multiple backing and inclusion processes for different blocks. That's what really important, right? For the same parachain block, it cannot happen synchronously. So it has to happen in different relay chain blocks. But for multiple parachain blocks, it can happen, asynchronously, which is extremely, extremely interesting. So I suggest if you want to read a bit more, check the article that Rebecca shared in the chat. It is really, really well explained. But I want to get to the last point of the presentation, which is basically, how this affects parachains, right? This was a little bit of the theory of how this works, more or less, high level. But let's talk about how this changes parachains. But before we do that, let's understand the different parameters that you have for asynchronous backing. You have something that is called candidate depth, which is a number of parachain blocks a collator can produce without them being included in the relay chain. Okay, so for example, this block was included here, but I can start building my parachain block without this being included. Okay, so that is called candidate depth. And then you have ancestry length, which is basically the oldest relay chain block you can anchor to, you can use as a reference for your next parachain block. And this means that you can actually run synchronous backing by running a synchronous backing with the parameter set to 0, because if we remember, we can only build on the latest relay chain block in a synchronous backing. We cannot build on top of an older block. And this happens sequentially, right? So we need this block to be included in order to produce the next block. But
Can I interrupt you with a question? Saffron has basically asked, I'm going to paraphrase the question, why was this process done synchronously at first? Why is this a new concept? Are there downfalls to asynchronous backing?
That's a really good question, to be honest. I would say that you would have to ask Parity. I would probably say that this is really, really complicated to code. And you have to do a lot of assumptions and things like that. And so if you think about this diagram, I was just looking at the question just to try to read it myself, but let me go back. This diagram is way more simple, right, at the end of the day, because a collator, a block producer, it's also running a relay chain. And so it can actually check, okay, the block was included. Let me just create another one. Okay, the block was included. Let me just create a new one, right? I think async backing was always in the roadmap, but it was just basically a future thing. It was a future feature more than a must feature to launch, right, at the end of the day. But yeah, I mean, think that asynchronous backing was a feature that it was worked on for years. It was not like, let's do a sprint, 1 month, 2 months, and we'll launch it, right? It was a feature that took a lot of years to develop, and it was really, really, really tough. So does this method increase gas fees since there's extra validation involved? So I want to make it clear that there's no extra validation. At the end of the day, the validation process of a block is the same. There's extra validation because now you're doing more validation in terms of like longer validation, but there's no like extra work being done. At the end of the day, that's all sort of like in the consensus model itself. Actually, if you think about it, there's now less fees in Moonbeam because you have more capacity, right? And more capacity means that the network is less utilized using the same resources at the end of the day, right? And so the gas fees are actually a little bit lower on the Moonbeam side. On the Polkadot side, these models are going to run into what is called Coretime now. And so the sort of consensus model is changing a bit. And it is hard to say if it's going to be more expensive or not, right? But at the end of the day, it's just basically, it's not that you have to run beefier machines or something like that to be able to do the validation, right? But it's a super, super good question, Adam, to be honest.
This sort of goes back to a question that I tried to answer earlier, but it would be better if you could. Do blocks that have been backed and included, so they've gone through backing and inclusion, do they get validated again, or is that like do they not need to be checked again?
So, I mean, there is a process in the inclusion process. Validators will verify the work of the subset of validators, right? So let me go back to one of the images that I had here, right? So you cannot rely on only these two guys for the security of the network, right, of the parachains. Because if not, it would be really, really tricky, right? It would not be really that secure. So at a very high level, what happens is that these validators have a stake in the Polkadot security system. And if other validators are randomly checking, because I do randomly check the work done by these guys, they check it was malicious. These two get their stake slashed 100%. And so that's how it happens at a very high level, right? And so, yeah, hopefully that sort of answers your comment, Rebecca.
Yeah, that's great. Thank you.
Yeah, no worries. All right, so let's talk about, async backing for Moonbeam, right? And so we know that we have faster block times because of what I said before. Now you don't have to wait for the inclusion. That backing takes 6 seconds, inclusion takes 6 seconds. You have to wait for both processes to propose another block. And so now you don't have to wait for the inclusion, so you can do a parachain block for every relay chain block, right? And so now, instead of 6 seconds, instead of 12 seconds, you have 6 seconds. This means that you increase capacity by 2x, right? Because, in a minute, you're producing more blocks, you have 2x capacity. The execution time, right? We talked before that all the transactions in Moonbeam could only happen in 0.5 seconds, let's say 50 million gas. But now we can actually increase that to 2 seconds. That means that we have a 4x increase in capacity, right? Because we have 2x increase because of faster block times, and now 4x because of the execution time, which theoretically means that we have 8 times more capacity from transactions per second perspective, right? That's in a very theoretical, mathematical, perfect world, okay? However, remember what I talked about the POV. So the POV is the information the collator, the block producer, shares with the validator to check that everything was valid, was okay, okay? But the POV size remained the same, okay? And so we have 8 times more theoretical capacity, but the data, the amount of data we can share with the validators, it was fixed at 5 megabytes. Don't ask why. You might ask why. I have no clue, to be honest. I should have had this question, but I think it's just a matter of time, right? I mean, you have a certain amount of time to be able to communicate with the validator, share all this information, and then the validator will verify it and will run it and will check it by itself. And I think it could be related to that. Maybe in the future we can increase the POV. I think actually there is plans to increase the POV, but with async backing, it sounded very promising of like, oh, we will have 8 times more capacity, but you have the POV remaining the same. And so, there's certain limitations, right? And so let me give you an example of a POV, okay? So imagine you're interacting with a very, very, very big smart contract on Moonbeam. It's a huge smart contract. It's millions of lines of code. It's extremely long and complex, but there's a function in that contract that adds 2 numbers, right? You provide one number, another number, and it adds them. That operation by itself, it's very easy, right? It's not going to take a lot of execution. The execution that it's going to take is probably very, very small. So just a little bit of gas, that's it, right? But the POV for that is going to be very big because you need to tell the validator of Polkadot, hey, this is the transaction, and this is the contract, and you send a bunch of bytes of the contract because the contract was very big, very heavy, and so you share the contract, and that it's a big POV. Even though the execution was very, very fast and very easy, but the POV in this example was very big because the contract was super, 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 super complex. Okay, so this is a good example of why the POV remaining the same. It's kind of problematic because yeah, you can put a bunch of new transactions, but if the contracts, for example, are very big, you're still limited by the POV, not by the execution time. And so I wanted to sort of explain a little bit this with some numbers, okay? And so this is before and after asynchronous backing on Moonbeam, okay? So remember the execution deadline. The execution is the amount of time you had to execute all the transactions on the network, which is before async backing was 500 milliseconds, and after is 2 seconds now, or 2000 milliseconds. There's actually something called block utilization threshold, which you don't actually use 500, you use 75% of it, which is 375 milliseconds. And this other 25 seconds, I think, is done for operational tasks, XCM, other things that are reserved for other things, okay? This means that before async backing, you had 375 milliseconds, and after you had 1500 milliseconds. If you correlate these two values to gas, so 500 milliseconds referred to as 15 million gas units. There's some constants here at the top right if you're interested in learning more. And this means that a single transaction, a single execution could have 13.5 million gas units. After async backing, you have 54 million gas units per single transaction. But the POV, remember the POV, right? It was the size of the chunk that you share with the validator to verify the state transition remained the same, okay? And because it remained the same, the gas per byte of POV had to be increased from 4 to 16, right? Because now this 13.5, or let's do a bit round numbers, it's easier. 15 million gas units are represented in 5 megabytes. So this means 4 gas per byte, but now you have 16 million gas units, but 5 megabytes. So now each byte of POV represents 16 gas units, okay? So the POV, every transaction that, every transaction that is related to POV, it is now way more expensive, okay? And so let's go through some numbers, okay? Some examples here. I don't know if there's any questions. I'll do a pause just in case there's any questions related to that.
There's one on numbers, but let's save it to the end and finish off with a little Q&A.
Okay, cool. That sounds like a plan. Yeah, I'll be sharing the slides as well. No worries. Slideshow. All right. So this is a simple ERC20 token transfer, right? So let me click on it so you see it. This is my token in the testnet, which is called Alberto token. This is a testnet token. No, this is not a pump and dump scheme or anything. This is a testnet token for educational purposes. And I did a transfer from myself to myself. You can see that this transfer consumed 93,000 units of gas. And yeah, that's the transfer, right? That's it. So this transfer used 0.002338 milliseconds of execution time. So of that 0.5, let's talk before async backing, we use 0.002 milliseconds of the execution time. The POV in terms of time, if we talk about the time, the gas or time or whatever that it takes, it's very small. It was a very small POV of this number that I'm not going to read it out loud. And if you check the opcode by opcode gas consumption, right? So if you go a little bit low level on the EVM and you calculate the gas that this transaction consumed, it's actually very small. Like I said, it's super simple because it's a super simple ERC20 token, which consumed 8,000 or 9,000 units of gas, okay? If we put that into perspective, the POV in terms of gas was 23,000 gas units, okay? The trace in gas was 29,000 units of gas. This is this number adding 21,000 units of gas, which is the baseline for Ethereum transactions. And then Moonbeam has a very special thing called MBIP5, which is basically a gas measurement related to the change in storage. So if you created a lot of storage, every byte that you create in storage can be represented in gas, okay? But this is in the Parachain state, okay? This is not in the POV. This is in the Parachain state itself. And these two things, POV and MBIP5, are related, but they're not identical, okay? And so you can see that the gas consumption, it's limited here, not by POV, because the POV was very small, not by execution time, which is the execution of the transaction, but by the amount of storage we're actually creating on Moonbeam, okay? And that's why the gas is actually 93472, which is this value right here, 93472, okay? And so this means that a simple ERC20 token transfer before async backing, we could do 160 in a single block, and after async backing, we can do 641. So it's not 8 times more, which is actually this value here. If it's only by execution time, it's a little bit less than 8 times more, but it's still a good improvement, right? It's from 160 ERC20 token transfer, now we increased it to 641. That's a pretty decent increasement, 5x probably, more or less 4x. That's pretty good, I would say. Nevertheless, if we go to another type of transaction, which in this case, this is a Moonbeam transaction, by the way. this is an interchain transaction. So I think it's Axelar moving remark tokens. So it's using Axelar, it's using a very heavy contract in Axelar. It's a very complex interaction. So you can see the numbers here, in which now the ref time was this amount of milliseconds. The POV was way bigger. I don't know if you remember the other name, but the other number, but it was way bigger. And the amount of execution was 108,000 instead of 8,000. So it was a lot more, it was heavier, this transaction. It used more resources. But if we go and look into this table down here, the main limited was the MBIP5 and POV, because like I said, these two are related. So POV is very related to MBIP5, MBIP5 is not related to POV. So you can see that the POV was the limited factor here in this type of transactions, which means that with async backing, we don't really see an improvement, right? So if I'm a marketer and I want to sell you basically async backing from Moonbeam, I'm going to try to find transactions that can give you this value here, that are limited by trace, by execution. So like a mathematical operation, like I showed you, adding two numbers. Adding two numbers, if it doesn't write anything in state, it doesn't change the state, it just adds two numbers, we're probably going to be able to do a lot more, 8 times more of adding numbers, okay? Because it's purely execution. It's just purely using computational power. But in this particular transaction, we're using a very heavy contract where, you know, the collator needs to provide a very big POV so that the relay chain validator can do the state transition with this very heavy contract. And so we see no real improvement by adding async backing. And so, yeah, I wanted to show you this example because if you're building on top of a parachain, you know, async backing is great because it gives you 6. I mean, we're still seeing an improvement as well because we have 6-second block times, right? So this is not really true. We should probably multiply this by 2. But what I'm trying to say is that the increase of execution time is not always reflected in the amount of transactions that you can actually process, okay? Just because it depends on, like I said, the POV, and hopefully this gives you a little bit of light into how parachains are affected by async backing in the good way, but also how it's still there's some other limiting factors outside of async backing that it's not allowing us to use the full potential of async backing. So, all right, that's all I had for you. We're on time, so that's perfect. I don't have any questions then, and we can call it a day. I was just kidding, but if you want to read the slides, you can check this QR code. This is the bit.ly link if you don't want to scan the code. Please check the websites, Moonbeam Network, Foundation. You can check the docs website as well. This is a Twitter, Telegram, Discord. You can ping me in Telegram if you have any questions, or Twitter. I'm not super active in Twitter, but I should be more active. But yeah, thanks a lot for everything. Thanks Encode Club for organizing this Educate series. And yeah, I don't know if there is any more questions.
There's a couple of questions. I'm going to do them out of order because the first one is, what is Moonbeam?
So Moonbeam is a parachain in Polkadot, right? So it's one of these parallel blockchains that is running in Polkadot, and we do smart contracts. So I don't know if you know, but in Polkadot you cannot really build applications. Applications, you build them on these parallel blockchains that Polkadot has, and Moonbeam is one of them, in which we are fully Ethereum compatible. If you build anything on Ethereum, you can port that direct application directly to Moonbeam without making any changes. So we try to replicate the Ethereum sort of environment and tooling and everything, and you can use that on Moonbeam straight away. So, I mean, if you want to read more, I'll suggest you to check the website, or you can ping me in Telegram, and we can discuss there.
Husni earlier asked a question that I said we'd save till the end. How does a collator estimate its target block execution time? Because from what they understood, it can vary between like 2 seconds on one block and 0.5 seconds on another.
Yeah, that's a great question, and this goes back to one of the earlier things that I mentioned, that all parachains need to do something called benchmarking. Okay, and benchmarking is the process of going through every single possible call that you can do on Moonbeam, and then measure in the amount of time it takes to execute that call in a specific machine, right? Let's say that, like I said before, it's running Windows 98 with 2 gigabytes of RAM and an Intel Pentium 2, and then you run the transaction there, and it takes 1 second because it's an old machine, and then you say, okay, a balance transfer takes 1 second. We do it with a much high-end spec machine for sure. And so then, let's say, for example, like I said before, you had a balance transfer takes 0.1 second, then you can do only 5 balance transfers, right? So if you have 10 in the transaction pool, you know that you can only do 5, and you include 5. If you're actually running a way better machine than the standard, you're actually going to not take 0.5 seconds. You're going to take 0.3 maybe, right? But the problem is that if you're running a worse machine, a much worse machine, you're actually going to take 0.7 maybe, and then the relay chain is not going to accept that block, right? Because it's going to grab it, it's going to try to replicate it, and then, maybe you didn't measure it correctly at the end of the day, and so it's not going to be able to do it, right? And so at the end of the day, that's how we do it. We basically say there's a reference time for every single transaction, and you have to be within the 0.5 or 2 seconds or whatever. So hopefully that clears it.
And Ivan has asked, how do you decide the block production time? Because your current block production time is 6 seconds, and you said it's possible to be like 2 for your mainnet chain.
Yeah, that's a really good question, right? And so right now, Ivan, we are limited by the POV, right? Because Moonbeam could produce blocks at 2 seconds, right? But at the end of the day, the validators are expecting a block from the Parachain every 6 seconds, okay? And so if we produce, let's say, 3 blocks within those 6 seconds, I'm gonna the collator is gonna say, hey, here are my 3 blocks. But all those 3 blocks have to fit within the 5 megabyte POV. And so you could, theoretically, this is not true, but theoretically you could run 0.1 second blocks or whatever. I mean, not really, like I said. But at the end of the day, you're limited between the amount of computation the validator can confirm or can verify, okay? And so at the end of the day, you just match the relay chain because of what makes more sense. But I know that, Basti was showing the other day, like, Parachains running at 0.5 seconds, which is super exciting. So theoretically, I think there's work being done to lower that. But right now, it's kind of hard-coded because of the limitations of the current system. So
thank you very much, Alberto, for coming in and making the time to come and give us this talk. It's been really, really interesting. I'll see you all next week. Enjoy the rest of your days.
Take care. Bye, Rebecca.
Everyone.
Take care.
Bye. Thanks.